Alright, today we're going to start working through our final exam review for semester 1. Remember, you are allowed to bring in your study buddy, so that is just your standard size sheet of paper, front and back. You can write whatever you'd like on it. It does have to be handwritten. We are collecting them before finals even start, so make sure it's in. Again, it should be in your teacher's possession no later than the end of class on Tuesday, 12/16. There will be a multiple choice and a show your work section. Let's jump into kinematics. This will be some review. Generally, whenever there's an explanation, I'm just going to talk through the explanation instead of write out every single thing that I'm saying. Number 1, the slope of a xt graph, that's a position versus time graph, represents the velocity. And the slope of a velocity time graph represents the acceleration. Define velocity. This is really displacement over time. You travel some distance in some amount of time, divide them, boom, you have your velocity. Difference between velocity and speed. Velocity is a vector. Speed is a scalar. This means, well, velocity, it has magnitude, that is the strength, and it has direction. That is, of course, the way that the velocity is going. What direction are you moving? Whereas a scalar, like speed, only has the magnitude. So, for example, if someone is going in a circle, say you are driving your car, and you are just turning in a circle constantly, and your speed, how fast you move, is not changing. So you're driving in a circle at 15 meters per second. That's your speed. Your speed is not changing. But your velocity is, because that direction piece, which way you're moving, is a part of velocity. And even if you're going the same speed, the number, the direction changing means your velocity is changing. Acceleration, well, this is really the rate of change of velocity. It's how much the velocity changes every second. There's 3 ways to accelerate. You can speed up, you can slow down, or you can change directions. Those are all some form of changing your velocity, which is acceleration. Let's make sure we're still recording. An object is moving in the positive direction and getting faster. Is the acceleration positive or negative? Here, what I like to talk about for finding direction of acceleration, or speeding up or slowing down, is there are really 2 different ways to have it. You could have the acceleration and velocity pointing the same direction. So they both point right, or you could have them both, say, pointing in the negative direction. Boom, there's your acceleration, there's your velocity, and these are always going to result in you speeding up. So if velocity and acceleration point in the same direction, you speed up. Let's move this on over. So the reverse is true, right? If you have an acceleration to the right, but the velocity is to the left, you're going to slow down. Of course, you could flip-flop this. Imagine the reverse situation, where you have an acceleration to the left, that'd be a negative acceleration, and you have some rightward positive velocity. This is going to result in slowing down. So these are our differences. If you have the acceleration and velocity match, if they go the same direction, you speed up, and if they point opposite directions, you are going to slow down. Let's use that for our next few questions. Number 6, an object is moving in the positive direction, getting faster. Okay, they're speeding up. The velocity is positive. That means, well, they're speeding up. Acceleration and velocity point in the same direction, so the acceleration would be positive. 7, an object is moving upwards and getting slower. Okay, slower means they're going to point opposite directions. If the object is moving upwards, they have a velocity upwards, that means the acceleration is going to be downwards. I'll just go ahead and circle that. Object is moving in the downward direction, getting faster. Okay, getting faster means velocity and acceleration match. They point the same direction. They are moving downward, so acceleration must also be downward as well. Car is traveling north and getting faster. Okay, getting faster, velocity and acceleration match. Car is traveling north. North must be that acceleration as well. Car is traveling down a ramp, getting slower. That means velocity and acceleration are opposite. If it's traveling down the ramp, it has a negative velocity, so it must have a positive acceleration. That would be an upward acceleration. 3 kinematic equations. All right, we can do this. Delta x is initial velocity times time plus 1/2 acceleration times squared. We also have final velocity equals your initial velocity plus acceleration times time, and final velocity squared equals your initial velocity squared plus 2a delta x. These are, of course, on your equation sheet. Remember how in projectiles you can split these equations into different directions. You can use them for the x, you can use them for the y direction. Variables and units. Well, we'll start off delta x. This is your displacement. This is change in position of the object. If you run around a track and you end up in the same position you started, your displacement is 0 because the position didn't change at all. VI, that is your initial velocity. This one's pretty self-explanatory. It is how fast you're moving at the beginning of the motion, at the beginning of the problem. Final velocity, VF, this is the velocity of the object at the end of its motion, whatever that motion may be. A is your acceleration. And T is time. Now, of course, we can add units to each of these, because it does say state units for each. We'll do that in purple. No better color for our units. Displacement is in meters. Initial velocity, meters per second. Final velocity, meters per second as well. Acceleration, meters per second squared. And T is in seconds. The car slowly comes to a stop moving in the positive direction. Okay, we need to keep in mind we're moving in the positive direction. We're coming to a stop. Stop means that the slope should be 0. We're moving in the positive direction. This would look something like this, where we eventually level off, coming to a stop. We're moving in the positive direction. The slope was positive. Remember, a changing slope. Slope is velocity on a position time graph, so a changing slope means a changing velocity. A car quickly accelerates from rest in the positive direction. All right, we're accelerating, we're speeding up is how this word is used in this sentence. So, we're starting at rest. Rest is just flat, right? Slope is your velocity, so if we're at rest, our slope to start out with should be 0. But we're not at that velocity forever. It's changing. We're speeding up. The slope should get steeper. In the positive direction, we're speeding up. Remember, a steeper slope on a position time graph means a faster velocity. A car starting at a positive position is at rest for a few seconds. Then the car accelerates in reverse and eventually passes the origin during this acceleration. Okay, this one's a little complicated, but we're starting at a positive position at rest. Positive position at rest. The position is not changing, hence no slope, it's flat. Car accelerates in reverse and eventually passes the origin during this acceleration. So we're moving backwards, we're speeding up like this. Remember, speeding up, you should go from a shallow slope to a steeper slope. And we have passed our origin. Velocity time graphs. Remember, velocity time graphs, the slope is your acceleration. Biker traveling constant positive velocity. Well, constant velocity, your velocity is not changing, so you shouldn't go up or down on your graph. Slowly coming to a stop, moving in the positive direction. Remember, positive is above the x-axis, negative is below. We're continuously moving in the positive direction, we're just slowing down. So we have a graph that looks like this. And it does say we're coming to a stop, so eventually we will reach our 0. That is along our x-axis. This whole time, What often gets mixed up is position time graphs and velocity time graphs, because this same shape on a position time graph would indicate an object moving backwards at some constant velocity. But this isn't a position time graph, this is velocity time graph, where this shape indicates, oh, we have some constant negative slope, some constant negative acceleration. We start off up here, moving really fast forward, and we gradually slow down. C, a car quickly accelerates from rest in the positive direction. Again, acceleration is the slope on a velocity time graph. We're starting from rest, so we should start from our 0 velocity, and we're accelerating in the positive direction, speeding up. A car starting at a positive position at rest for a few seconds, then the car accelerates in reverse and eventually passes the origin during this acceleration. So we start out at rest. That would be right here. And then we say, okay, we're accelerating in the negative direction and eventually pass the origin. Notice how 12 and 13 are synced up, right? Graph A and graph A, these are the same motion. The graphs look very different. B and B, same motion represented by very different looking graphs. You might ask Mr. Rosauer, in D, where did you include starting at a positive position? Where did you include passing the origin? Well, on a velocity time graph, you actually cannot include starting at a positive position. There is no place for position on a velocity time graph. All you can tell, for instance, let's look at this graph right here. All you can tell from this graph is there's an object moving at a constant speed. It is not accelerating. Where did it start, right? Maybe we call the origin some tree. Maybe the car starts in front of the tree. Maybe it starts behind the tree. Maybe it starts at the tree. There's no way to tell where we start from a velocity time graph. We cannot represent it from a velocity time graph. All right, moving on to page 2, position time graph. Sketch the position time graph for the following. A biker traveling at a constant positive velocity. Remember, rules for position time graphs. This is a great thing to study and review, or maybe write on your study buddy. Position time graphs, the slope is the velocity. So if you're at a constant positive velocity, well, that means you must be at some constant positive slope. So that could look like this. Alright, continuing on. Number 14, explain what is happening in the position time graph at each segment label. Well, we'll just talk through it. So, at A, remember something very, very important on a position time graph. So, on X versus T graph, the slope is the velocity. So, segment A, we have a positive slope, so a positive velocity. The object, the person, whatever it is, they're moving forward. Their position is increasing. B, they have a positive velocity, but they're slowing down. You can tell because the slope gets less steep. Again, the slope is the velocity, so if the slope gets smaller, the velocity gets smaller. C, they're at rest. They're not moving, the slope is 0. D, they have a negative velocity, and they are speeding up. The slope is getting steeper. Negative because it is a negative slope. E, negative velocity, constant velocity. At this point right here, they reach back to where they started, the origin. And then they go backwards from there, right? They're still moving backwards. Some negative constant velocity. At G, they are at rest. And H, they're moving forward at some constant velocity. Explain what's happening in the velocity time graphs. Okay. A, we have some constant velocity. I'll write CV for a constant velocity, and it is negative. At B, they have a negative velocity. They're slowing down. Recall that on a velocity time graph, the closer you get to the x-axis, the slower you are going. Because at the x-axis is our 0 velocity. Above the x-axis is positive, below the x-axis is negative. So A is a constant negative velocity. B is a negative velocity. You're moving backwards, but you're slowing down. C, now you have a positive velocity. You're speeding up. You're getting farther away from the x-axis. D is a constant positive velocity. And E, we are slowing down. It is a positive velocity, and we are slowing down. Alright, a lot of these, let's talk through. Newton's first law. This is the law of inertia. So objects in motion tend to stay in motion. Objects at rest stay at rest unless there is some external unbalanced force. Newton's first law can be used to support an explanation as to why you lurch forward on a bus when it brakes. Well, you have inertia, you are moving with the bus stops moving, but you don't stop moving until there's some external force to stop you. So that could be the seatbelt, or that could be, say, you hitting the seat in front of you. 18. You feel pushed against the passenger door. Well, you take a sharp left turn. The car moves sharply to the left, but you were moving in a constant speed in a straight line. You're still going forward. The car moves to the left. You're still going straight. You end up hitting the door because you were going straight and the car moved. When you hit the door provides that force to change your direction. Even though the moon orbits at a constant speed, there is still a total force. Well, the moon is orbiting in some circles. So if this is the Earth, here is the orbit of the moon. The velocity of the moon is constantly changing. So here's the moon, it would be moving like this. Here's the moon, the velocity, even though it's the same speed, it's moving at the same speed, the direction changes. This is still an acceleration. So there needs to be some sort of total force to cause this change in motion. Newton's third law is that every action force has some reaction force. So for example, if I hit my hand on the table is going to hit my hand with the same amount of force that I hit the table. If you are hammering in a nail, the hammer hits the nail with the same force that the nail hits the hammer. Same force, opposite direction. Foot kicks soccer ball. Which is greater? They're equal. Newton's third law. Foot kicks soccer ball. Which force happens first? They happen at the same time. Person pushing a shopping cart. While they are pushing the cart, there are 4 forces on the cart. Write all 4 forces in the form FA on B on the cart. Then identify the 4 corresponding forces that complete. Okay. Force of cart. All 4 forces in the form FA on B. Okay. Force of gravity. So this one is going to be the force of gravity. This one is going to be the normal force. This one is going to be the applied force, and this one is going to be friction. Force of gravity would be the force of the Earth on the cart. Newton's third law pair would be the force of the cart on the Earth. The normal force. This would be the force of the ground pushing on the cart. This then would be the force of the cart pushing on the ground. The applied force. This is the force of the person pushing the cart, and then the force of the cart pushing the person. And friction. This would be the force of, we could say the surface, right? We've already said the ground, so let's say the surface on the cart and the cart on the surface. Father pushes their child. There's a force of the father on the child and a force of the child on the father. They are equal, so they don't cancel out and result in no total force. Well, the forces act on different objects. Say you are pushing on some box. You apply a force on the box. This is the force of you on the box. We could say this is A on B. Well, that same force gets applied to you, not the box. This is the force of B on A. So the forces happen on 2 different objects. Both equations for the force of gravity. Okay. Find each variable, write the units. Equation, Fg equals mg. M is mass, measured in kilograms. G is the acceleration due to gravity, measured in meters per second squared. We have also used force of gravity is universal gravitational constant, m1, m2, if it will let me write, over r squared. G, and we'll separate these out, capital G, universal gravitational constant. M1 is just mass 1, measured in kilograms. M2 is mass 2, measured in kilograms. Keep in mind it doesn't matter what you call M1 and M2. It just matters that you keep it consistent. So if you have a person and the Earth, make sure M1, whatever you define as M1, stays M1. R, you'd like to think it's the radius. It is not. It is the distance between the object's centers. And that is, of course, measured in meters. Now you might say, oh, what are the units on G? Units on G are a little tricky. Recall, force is measured in newtons. We need units of newtons. Newtons is on the left-hand side, newtons must be on the right-hand side. So the units of our universal gravitational constant are newtons, but we also have r squared on the bottom. We want to cancel those units of meters. That would be meters squared. So we put meters squared here to cancel out our meters squared on the denominator. We have kilograms and kilograms. We want to cancel those, so we put kilograms squared on the denominator. When you see this value, it is given on your equation sheet, 6.67 times 10 to the negative 11th, Newton meters squared per kilogram squared. You do not plug anything in here. Those are just units. Force of gravity on the Earth from the Sun. Alright, so we're going to use our big equation, right? Fg is g m1 m2 over r squared. Let's make sure we're still recording. Okay. Capital G, 6.67 times 10 to the negative 11th. M1. Well, the Earth was listed first, so I'm going to make M1 the Earth, mass of the Earth. 5.98 times 10 to the 24th. M2 from the Sun. The Sun is 1.99 times 10 to the 30th. Now, distance from the Sun. We can see we get this. So that is what we will put. Distance between the two objects. Now, we'll also talk about something else. Alright, now that we've got this set up, don't forget this is squared on the denominator. Let's go ahead and practice scientific notation in our calculator. 6.67 second, and you hit this comma, that EE button. After EE, you enter your exponents. Our exponent is negative 11, we enter it. I like to just hit enter, make sure that the calculator got it. If it was not input correctly, it will give you an error. Then we'll multiply by 5.98, EE, 24. Multiply by 1.99, EE, 30. We have a very, very, very big number. Now we go ahead and let's divide by, and I'm going to put this in parentheses, 1.5 EE 11, and we're going to square that. And we get 3.5 times 10 to the 22nd. Don't forget your units. This is a force, so it must be in newtons. We're going to do the same process, right? We get lots of practice. Force of gravity, Saturn from the sun. Same equation. Plug in your G, that's a universal constant. It's not going to change. Saturn, what is Saturn's mass? 5.67 times 10 to the 26 kilograms. The sun's mass, we used that before, 1.99 times 10 to the 30th. And we will divide by the distance, Saturn to the sun, 1.43 times 10 to the 12th. And we're going to square that. Again, entering this all in, 6.67 times 10 to the negative 11th. As you do more and more of this, you'll get pretty quick. To the 26th times 1.99, 10 to the 30th, and then we're going to divide, put it in parentheses, 1.43 times 10 to the 12th, and we're going to square that. 3.68 times 10 to the 22nd. Gravity on the sun from Saturn. Well, Newton's third law says the force of A on B must be the same size as the force of B on A. So, the force of gravity on Saturn from the sun is the same as the force of gravity on the sun from Saturn. So it must also be 3.68 times 10 to the 22nd newtons. Alright, lovely. Make sure we're still recording. Excellent. The 2017 Honda Civic, approximately 1,200 kilograms, was on the surface of Mars. What would the force of gravity be between the car and Mars? Okay. Well, we'll use our big equation. We have 6.67 times 10 to the negative 11th. The mass of the Honda Civic, 1,200 kilograms. The mass of Mars, 6.37 times 10 to the 23rd. Divide by the distance between their centers. Well, if you're on Mars, here's an artistic rendition. Here's the center of Mars. Here is your car. We're just going to say, since Mars is so huge compared to your car, we're going to say the radius of Mars is really the distance to your car, right? We don't have to add in the extra, say, half a meter that the car is off the ground on its wheels. We'll just say the radius of Mars is already so huge, that's going to be good enough. So plug in the radius of Mars. Again, that's not what r is, it's the distance between the two object centers. But since we're on Mars, the distance between the two centers is approximated as the radius. 3.43 times 10, I believe that was to the 6th, indubitably. Let me go through, again, that is squared, and I closed my calculator too quickly. Let's grab it again. There we are. And once more with feeling. Negative 11th times 1,200 times 6.37, 27, divide by, put it in parentheses, 3.43 to the 6th, and square. Aha! I knew that was too high. It's always good to double check. And see, this number is way huge. Right? If you imagine what's the force of gravity on a Honda Civic on Earth, 1,200 times 9.8. That's not going to be nearly this huge. So if you get a weird answer, and if your answer doesn't make sense, double check. I plugged in 6.37 times 10 to the 27th. That was my mistake. Couldn't read my own handwriting. So, let's fix that. This is to the 23rd. Okay. And we will redo our calculations. Let's clear this out. 6.67 times 10 to the negative, not 41, negative 11, excellent, times 1200, times 6.37, times 10 to the 23rd, divide by 3.43 times 10 to the 6th squared. That makes much more sense. 4,333 we'll round it to 7 newtons. One more. Force of gravity on an astronaut on the International Space Station orbiting Earth with an altitude of 400,000 meters above the surface. Okay. Fg. 6.67 times 10 to the negative 11th. Mass of the astronaut, 92 kilograms. Mass of the Earth, 5.98 times 10 to the 24th. And we can then divide by the distance between the two object centers. Be very careful with this one. The International Space Station is not on the surface of the Earth. We have to say, if we take our drawing from before, it is somewhere out here. So distance between the two object centers will be the radius plus the distance the International Space Station is off the surface. We know the radius of the Earth is 6.37 times 10 to the 6th. So we can say, okay, 6.37 times 10 to the 6th plus our 400,000 meters. And we're going to square that. So we go through 6.67 times 10 to the negative 11th times 92 times 5.98 times 10 to the 24th and divide by, again in parentheses, 6.37 times 10 to the 6th plus 400,000, square that, 800. Again, does this number make sense? Yes. Force of gravity of someone 92 kilograms of mass on the surface of the Earth would be 92, their mass, times g, 9.8, 901. They're farther away than the surface of the Earth. Gravity gets weaker as you get farther away from the surface, so it should be something less than that 901, which is exactly what we found. Alright. A 4 kilogram sled is pushed by a child to the right on frictionless ice from a speed of 3 meters per second with a force of 20 newtons. Alright, we got a lot of stuff to take care of. Complete the table below. Forces acting on the sled, written in FA on B format. Okay, let me do the free body diagram of the sled first. Here we are. We know there's going to be a force of gravity there on Earth. There will be a normal force since they are touching some surface. There is an applied force, right? It's pushed by a child to the right. So we say, okay, that's our free body diagram. Forces acting on the sled. Okay, we already did that. Normal, applied, and gravity. Forces acting on the sled, A on B format. Okay. There's the force of the ground on the sled. That, let's move this a bit. That is the normal force. There's the force of the Earth pulling on the sled. That's gravity. And there's the force of the person pushing the sled. That's our applied force. Okay. Are the forces in the x direction balanced? Well, there's no force to the left, so they cannot possibly be balanced. Are the forces in the y direction balanced? Yes. But the sled is not accelerating vertically, so the vertical forces must be balanced. Is there acceleration? Yes. We can even draw in normal force and gravity are balanced with our little tick marks. What is the direction of the acceleration? Well, forces are unbalanced in the x direction. Unbalanced forces cause acceleration in the same direction of the unbalanced force. So, the unbalanced force is to the right, the acceleration is to the right. Is the speed of the object changing? Yes. It is accelerating, and in this case, speeding up. It's getting faster. Is the total force 0? No. What forces are in the same direction as the total force? The applied force. None are in the opposite direction. What direction is the total force? Well, normal and gravity cancel each other out. They're balanced. Applied force is to the right. The total force is to the right. Solve for the acceleration. Show all steps. Okay, well, total force. Really, your general steps to solving a forces dynamics problem. You're going to draw your free body diagram. That's step 1. Then you will write 2 equations for total force. I will step them out as steps 2 and 3. First one is Newton's second law. Total force is mass times the acceleration. Your second step is to write, total force is just the sum of your forces. You ignore the ones that cancel out. Normal and gravity are balanced. You don't list them. But the applied force, you're going to list. Positive forces you list as positive. Forces in the negative direction you list as negative. So total force is our applied force. Then step 4, combine these 2 equations. F total is ma. F total is also the applied force. So the applied force is mass times the acceleration. We know from our problem the force is 20 newtons. That gives you the applied force. What else are we given? The mass, 4 kilograms. Plug that in. Solve for the acceleration by dividing both sides by 4. If we do that, we find, our acceleration, 20 divided by 4, is going to be 5 meters per second squared. We can be really specific. We could say, well, the force, that total force is to the right. Acceleration and total force always point in the same direction. So that acceleration is to the right. Velocity of the sled in the y direction, it's not moving vertically. It's not going up, it's not going down. It's just pushed across some surface. So the velocity should be 0 and it should stay there. It is speeding up in the x direction. We are pushing it to the right from a speed of 3 meters per second. So we start at a speed of 3 meters per second. We can label that right here. And we are going to have some positive acceleration, like so. Our velocity in the x is increasing into a faster positive number. Alright, let's do this again. Forces on the puck. I'm going to start with the free body diagram. It is frictionless, that's important to know. There is gravity. 99% of the time, there will be gravity. Lots of the time, we will have a normal force as well, as long as you're on a surface. It is sliding at a constant velocity. It is not being pushed, it is just sliding. There's no friction. It is a frictionless surface. There's no applied force. No one is pushing it. There's no tension because there's no rope or string attached. So it is just normal and gravity. Well, there is the normal force, and there is the force of gravity. Force A on B format. Well, the normal force is really the ground pushing on the puck. And gravity is the earth pulling on the puck. Alright, forces in the x direction balanced. Yes, because there are no forces in the x direction, so they must be balanced. Forces in the y direction balanced? Yes, they are. We already identified that with our little tick marks right here. Is there acceleration? No. And we know this, well, from our forces, but also it was told it is moving at a constant velocity. Constant velocity means no acceleration. That's how we were able to know normal and gravity were balanced. If no, cross this box out. Heck yeah. Is the speed of the object changing? No, there's no acceleration. Is F total 0? Yes. The forces are balanced, the total force is 0. If F total is 0, cross it out. I will. Cross it out. Normal force acting on the puck. Okay. Well, just like we said before, normal force and gravity. You could skip a few steps. You could say normal force and gravity are balanced, and you just derive Fn equals Fg. You could also say, like we just did, write out F total is mass times acceleration. Write out F total is positive forces minus negative forces. Positive is the normal force. Negative is gravity. Normal minus gravity. Bear with me. Set these equations equal to each other. Normal force minus gravity equals your mass times acceleration. Well, we're at a constant velocity. The acceleration is 0. This whole term right here turns into 0. So, normal force minus gravity give you 0. Send gravity over to the other side. Normal force is equal to gravity. Now, of course, you can just look at your free body diagram, and you can know that, but that is a nice way where we derive this expression. So normal force is equal to gravity. We know an equation for Fg. It is m times g, the acceleration due to gravity. We know our mass, 0.08 kilograms. So the normal force must be equal to m times g. The mass is 0.08. G on the surface of the Earth is 9.8. If we take this with our calculator and we go through, we can say, all right, 0.08 times 9.8 gives us a normal force 0.784 newtons. Velocity of the puck in the x direction. It is moving at a constant velocity of 8 meters a second to the left. So we have some negative, right? We're saying the right is positive. So to the left is a negative velocity. I believe it was 8, we said, yes. Okay, so here is negative 8 for our velocity, and we will just maintain that constant negative velocity. Again, it's not moving in the y direction. Looks like here this should say y instead of x. We are at 0. Not moving up and down. 0 vertical velocity. Alright, elevator problem. This is where things start getting tricky with our forces. Alright, what forces act on us while we are in an elevator? We're moving upward, we're slowing down. Keep in mind, this is important. Moving upward. Positive velocity. We are slowing down. If you're slowing down, the only way that happens is if velocity and acceleration point opposite directions. So since we know our velocity is positive, our acceleration must be negative because we are slowing down. So that acceleration is negative 2 meters per second squared. Since we know we're slowing down, moving upwards, right, we have this negative acceleration. The only way that happens is if our downward force is larger than our upward force. We have normal force and gravity, but they are not balanced. What are the forces acting on you? Normal force and gravity. Again, normal force is the ground on you, and gravity would be the earth pulling on you. Forces in the x direction balanced? Yes. There are no forces in the x direction. Forces in the y direction balanced? No. We are accelerating. There is acceleration. What direction is the acceleration? Well, we're accelerating downward, right? We're moving up. We have some positive velocity, but we're slowing down. How do you slow down when you're moving up? Well, you have some downward acceleration. Speed of the object changing, yes. We are getting slower. Is the total force 0? No. Total force is downward. Must point in the same direction as your acceleration. What forces are in the same direction as the total force? Well, total force is downward. Gravity is in the same direction as the total force. The normal force is in the opposite direction. Solve for the force of gravity. Okay. Well, force of gravity is m times g. Show all steps. What is our mass? 60 kilograms. What is the g value on Earth? 9.8. And we go ahead, we plug this in. 60 times 9.8. 588 newtons. Alright, continuing on. Now we have our force of gravity. Again, just like we did before, we've drawn our free body diagram. Like we mentioned, that is your first step. Then we write our two equations for total force. We have Newton's second law. Total force is mass times acceleration. And we'll write our own custom equation from our free body diagram. Positive forces, subtract negative forces. Normal force minus gravity. Set the equations equal to each other. M times A equals Fn minus Fg. And now we know the force of gravity. So we plug that in, right? Force of gravity is 588. We know our mass, 60. And we know our acceleration, 2. More specifically, -2. So now we go ahead and we can say, okay, 60 times -2, that's going to give us negative 120. So we could rewrite over here, negative 120 equals normal force minus 588. Add 588 to both sides. We should get 468 is our normal force. And now, of course, that would be newtons as well. Can't forget those units. Velocity of u in the x direction. Well, we're in an elevator, we're not moving in the x direction, so our velocity should just be 0. And we are moving upward, but slowing down. So, we'll start at some positive velocity, and we'll come all the way to a stop. Right, starting at some positive velocity, moving upward, coming to 0. Another problem, a skydiver problem. Free body diagram. Well, we have gravity. Since we know the acceleration is 8.3 meters per second squared downwards, that's less than the 9.8 we'd expect if there was just gravity. So there must be a little bit of air resistance as well. We have the air resistance, and we have force of gravity. Gravity is the force of the Earth on the person. Air resistance is the force of the air on the person. Forces in the x direction are balanced? Yes, because there are none. Y direction forces are not balanced because we are accelerating. What direction is the acceleration? Well, down. And we were told that. Speed of the object is changing. Yes. We are getting faster. Total force is not 0. What is the direction of the total force? Downward. What forces act in the same direction as the total force? Force of gravity. What's opposite? Air. Force of gravity acting on the skydiver. Just like before, Fg equals mg. Mass is 80. G is 9.8. Plug this into our calculator. 80 times 9.8. 784 newtons. Force of air resistance. Okay, just like before. Start out with our free body diagram. We'll write our two equations. Total force is mass times acceleration. Newton's second law. And total force is your positive forces, and you subtract your negative forces. Air resistance. Let's double check, make sure we're saying down is positive. Okay, if we're saying down is positive, then our positive force is now gravity, and our negative force is air resistance. Now, do note, you could absolutely just keep saying downward is negative and upward is positive, and it will work out just the same. Now we can plug in, okay, gravity is 784 minus our air resistance. We know the total force is mass times the acceleration. So plug in 80 for our mass, 8.3 for the acceleration, and we can solve for that air resistance. 80 times 8.3. This gets us 664 equals 784 minus air resistance. And we can subtract 784 from both sides, and we get, okay, minus 120 equals our negative air. So air resistance is 120 newtons. There we go. All right. Some more skydiver stuff. 80 kilogram skydiver is falling from 15,000 feet. Draw and label a free body diagram of the skydiver the instant she jumps. No air resistance at this point. Well, if there's no air resistance, the only force would be gravity. If the only force is gravity, the acceleration due to gravity is 9.8. So the acceleration would be negative 9.8 meters per second squared. Total force. Well, only force is gravity. Gravity is mg. The mass is 80. G is 9.8. We just solve for this up here. 80 times 9.8 gives us 784 newtons. Acceleration in the skydiver when the air resistance is 400. Well, we know total force is mass times acceleration. We know total force would be air resistance minus gravity. Combine them, we get mass times the acceleration, that's what we're solving for, is equal to air resistance, 400, minus our force of gravity, 784. 400 minus 784, divide by our 80, and we find, the acceleration is negative 4.8 meters per second squared. That, of course, means it is downward. Sometime later, we would a parachute. Encounter an air resistance force of 3,550 newtons. Calculate the acceleration of the skydiver at this instant. Well, now we have our force of gravity, but that's much smaller than our air resistance. The equation is still the same. Mass times acceleration is equal to the air resistance minus gravity. The air resistance is now 3,550. Force of gravity is our 784. We know the mass of 80. If we go through, let me grab my calculator. We find our acceleration is positive 34.6 meters per second squared. So this, of course, means it is up. We got a positive number. We defined up as positive. Direction of the skydiver's velocity is down, right? They're still moving down even when the parachute is open. Write out both equations for friction. We have our static friction, in particular the maximum static friction, and that is that the force of static friction max value is the coefficient of static friction times the normal force. And then we have our kinetic friction, which is that our force of kinetic friction is the coefficient of kinetic friction multiplied by our normal force. Variables, well, mu s, that is the coefficient of static friction. Mu k is the coefficient of kinetic friction. Remember, static friction has a maximum value, but kinetic just has one value. Our coefficients, they are both dimensionless. They are not measured in any unit. It is just the coefficient, no units. If you put units on a coefficient of static or kinetic friction, it will be wrong. And then Fn, this is the normal force. Coefficient of friction is a representation of how rough a surface is. A child pushes a 14-kilogram box across a rough surface at a constant speed. Constant speed is key. That means our forces are balanced, no acceleration. Force of friction resisting the sliding is 35 newtons. Free body diagram of the box. Okay. Since we're at a constant speed, all forces must be balanced. Gravity must be balanced with our normal force. We have some applied force, and it must be balanced with our friction. And we can be very specific. It is sliding, so that must be kinetic friction, since kinetic friction is friction of motion. Normal force acting on the box. Well, from our diagram, we know the normal force is equal to the force of gravity. The force of gravity is mg. The mass of the box is 14. G is 9.8. So if we go ahead and plug in 14 times 9.8, we find that normal force and the force of gravity are 137.2 newtons. The applied force, well, from our diagram, right, everything's balanced. We're at a constant velocity, no acceleration, no total force. The applied force must be equal to kinetic friction. We're told the child pushes, or rather, we're told the force of friction is 35 newtons. So we know 35 newtons must be the applied force as well. And they push with 50 newtons. Calculate the acceleration. Well, total force is going to be the applied minus our friction. We can plug in MA is our total force, so it is applied minus friction. Now let's plug in. The mass is 14 kilograms. 14A. We're calculating the acceleration, we leave it. The applied force is 50 newtons. Friction does not change. Friction is 35 newtons. So if we go through 50 minus 35, of course we get 15, and then we'll take that and we will divide by our 14 for our mass. That will give us an acceleration 1.07 meters per second squared. Coefficient of kinetic friction. This, of course, we want to be specific. This is our kinetic friction. We know kinetic friction is 35. So let's use our kinetic friction equation. It is the coefficient of kinetic friction times normal force. Our force of kinetic friction is 35. The normal force, we solved this earlier, 137.2. Take 35, divide by 137.2, and we get a decimal. This is typical. Coefficients of friction are typically some decimal. They're small numbers. No units on a coefficient of friction. Farmer is trying to move his stubborn pig again. Force of gravity acting on the pig is 2,500 newtons. Farmer pulls with a force of 800 newtons. Pig does not budge. Well, if they don't budge, static friction must balance however much the farmer is pulling. So the force of static friction is 800 newtons. Total force, well, pig does not budge, there's no acceleration. Total force must be 0. Farmer pulls with 1,000 newtons. Still, pig does not budge. Static friction must balance that pull. Total force is still 0. Would you be able to, given the information, coefficient of static friction? You would not, because for static friction, right, we're saying the maximum static friction is equal to the coefficient of static friction times the normal force. You could find the normal force, because you know normal force and gravity would be balanced. So normal force is 2,500 newtons. But you don't know the maximum value of static friction. We know it's bigger than 800. We know it's at least 1,000. But we don't know what that maximum value is. If we know the maximum value, then we can plug in our maximum value, plug in our normal force, solve for our coefficient. Until then, we do not know. Alright, farmer pulls with a force of 1,200 newtons, pig begins accelerating. Coefficient of kinetic friction is 0.363, calculate the acceleration. You need the mass. Absolutely. Okay, so let's start out. Calculate the acceleration. Well, how are we going to get the acceleration? We know the total force is mass times acceleration. We know the total force will be our applied force minus that friction. We don't know what type of friction. Well, actually, we do. It's going to be accelerating. It's going to be kinetic. How can we find this? All right, we plug in MA. We know the applied force is 1,200. Friction, remember friction, kinetic friction, is our coefficient of kinetic friction times the normal force. Well, we have the coefficient of kinetic friction, 0.363. The normal force, we do not know. But if we drew out a free body diagram, we could say there's gravity, normal force balancing gravity, some applied force, and a smaller force of kinetic friction. Since the normal force is equal to gravity, normal force is m times g. How do we find the mass? Well, we were told earlier, force of gravity is 2,500 newtons. So, 2,500 newtons is our normal force. We can plug that in right here. That's going right here. And we can say, oh, that mass, well, we know G is 9.8. The weight, the force of gravity is 2,500. Divide by 9.8. The mass of the pig is 255.1 kilograms. Now that we have all this, plug in our mass. 255.1 acceleration equals our 1,200 minus 0.363 times 2,500. If we go through, do our math, 0.363 times 2,500, that gives 907.5. $1,200 minus 907.5 gives us 292.5 equals 255.1 divide, oh, can't forget A. And then we find the acceleration, 1.15 meters per second squared. Alright. Projectile motion, very specific situation we studied. Baseball player throws a baseball to their teammate When does a projectile motion begin? When does it end? Projectile motion is defined as the only force acting on an object being the force of gravity. So, projectile motion starts when the ball leaves the player's hand, and it ends when the ball is caught. So while it's in the air, while the only force is gravity, it is projectile motion. Why is the y direction acceleration negative 9.8? Well, go back to forces. Total force is mass times acceleration. Your total force for a projectile, the only force acting, is the force of gravity. The force of gravity is mg. Set these equations equal. Total force is ma. Total force is also, for a projectile, mg. Our masses cancel. And we find out our acceleration is simply g, or negative 9.8. Again, forces cause acceleration. For a projectile, the only force is gravity downward. There are no forces left or right, therefore there can be no acceleration left or right. Alright, here we have an angle, 33 degrees, speed of 100. Projectile eventually hits the ground. Write the values requested at each location. Okay. Here we need to break it into components. We have our velocity right here. It is at an angle, 33 degrees. Speed, 100 meters per second. Let's show you exactly how we do this. If we bust out our, come on, calculator. Make sure you are in degree mode. Once you've made sure, we know we have different components right here. Our component in the x direction is just going to be that velocity times the cosine of our angle theta. This component in the y direction is going to be our velocity times the sine of theta. So, 100 cosine 33. That is our velocity in the x. 83.87. What about that velocity in the y? 100 sine 33. 54.46. Now we can plug this in. Right after the lunch, velocity in the y. 54.46. Let's switch to a different color for funsies. Can never go wrong with blue. 54.46. Velocity in the x. 83.87. We'll tack on units, of course. In the x direction, the acceleration is always 0. We'll write units up here, so we don't have to write it every time. Acceleration, meters per second squared. Velocity, just meters per second. Our accelerations are never changing for a projectile. In the x, no matter where it's located, that acceleration is 0. In the y, no matter where it's located, that acceleration is negative 9.8. At the top of the arc, if our acceleration is 0, that x velocity is never changing. Now, our y velocity is changing. What's special about the top of the arc? Well, at the top, it's no longer moving upward, but it also hasn't started falling downward. Therefore, it must be 0 vertical velocity. When it reaches the ground, there's a special case, since it reaches the same height it was launched from. Your final velocity in the y direction is the same as the initial, but downward. Negative 54.46. You throw a ball straight up with a speed of 30. The acceleration due to gravity is negative 10. For this problem only, what is the ball speed after 1 second? Well, keep in mind what acceleration means. This is the change in your velocity every second. Every second, your velocity should decrease by 10, because our acceleration is negative 10 for this problem. So, you start with a velocity of 30. 1 second later, it is decreased by 10. It is 20 meters a second. 2 seconds, 10 meters a second. 3 seconds, 0 meters a second. It's at its peak. 4 seconds, negative 10 meters per second. What is the ball's speed when it comes back to your hand? We'll use the same knowledge we have here. When it reaches the same height it was launched from, it's whatever speed it was launched with, right in the y direction, but in the opposite direction. If it leaves your hand vertically, going 30 meters a second, it comes back going 30 meters a second, just in the opposite direction. How much time passes? Well, 1 second was 20, 2 was 10, 3 was 0, 4 was negative 10, 5 would be negative 20, 6 would be negative 30. 6 seconds passes. We know we're going to be using an acceleration of negative 9.8 for our problems, but approximating the acceleration due to gravity as negative 10, and using a trick like this every 1 second, that velocity decreasing by about 10, you can estimate how long something should stay in the air. Right? If you launch something and it has a vertical component, 30 meters a second, you know it's going to spend 3 seconds about going upward, and then 3 seconds about going downward. Alright, another section. Projectile is launched from level ground straight upward with a speed of 100. Projectile eventually hits the ground from the same height it was launched from. Write the values requested. Accelerations are never changing. We will put our units for completeness. Meters per second squared, meters per second, and meters per second squared. Acceleration in the x is always 0. Acceleration in the y, always negative 9.8. Velocity in the x. It is launched straight upward. Velocity in the x is 0. Velocity in the y is 100 to start. At the peak, it is 0. Coming back down, negative 100. Alright, 2.5 kilogram ball launched from the ground with a velocity of 20 meters per second at an angle of 35 degrees above the horizontal. Ball eventually reaches the ground again at the same height it was launched from. Okay. Let us grab our calculator. Alright. Acceleration at the maximum height. Well, it doesn't matter where we're located. It just matters what direction. Acceleration in the x is always 0 for a projectile. Acceleration in the y is always negative 9.8 for a projectile. What is the velocity at maximum height in the x direction? In the x direction, we'll have to find it. Let's find our initial velocity in the x and initial velocity in the y. Keep in mind, initial velocity in the x, that is going to be the velocity. Again, just as a reminder, initial velocity in the y, initial velocity in the x. In the y, that is your initial velocity times the sine of theta. In the x, that is your velocity times the cosine of theta. Our initial velocity is 20, so we'll go 20 times the sine of our angle 35 degrees. Initial velocity in, that was sine, so that's initial velocity in the y, 11.47. Initial velocity in the x, 20 cosine 35. 16.38 meters per second. At the maximum height in the x direction, well, there's no acceleration, so the velocity at the maximum height in the x direction is still 16.38. The velocity in the y direction at the maximum height was at the peak, so that would be 0. Not moving up, not moving down yet. Maximum height the ball reaches. For maximum height, we are going up. We're finding the peak right here. We know the velocity in the y is 0. We can make our x, y chart separate your variables. We're really going to use the y for this one. We know that initial velocity in the y. 11.47. We know the acceleration in the y. Negative 9.8. We know the final velocity in the y at the maximum height is 0. We want maximum height, delta y. So what we could do, we don't want time. There's an equation that lets us avoid using time. That equation is final velocity squared equals your initial velocity squared plus 2 acceleration delta y. Plug everything in. Final velocity in the y is 0. This turns into 0. Initial velocity in the y, we're just squaring that. 131.56 plus 2 times 9.8. This is negative 9.8 as well. So we're going to make this a minus sign. 19.6. Delta y is what we are solving for. Rearrange. This will end up being 131.56 divided by 19.6. And we get our delta y, that maximum height being 6.7 meters. Calculate the time it takes to reach this maximum height. Well, now, easiest one to do would be final velocity equals initial plus acceleration times time. Again, this is all in the y direction. Final velocity at the peak is 0. Initial velocity, 11.47. The acceleration is our negative 9.8, multiplying by time. This will be 11.47. Oop. Let's clear this out. 11.47 divided by 9.8. Our time to the peak is 1.17 seconds. Total distance. Total distance, you want to use the total time. Since we're landing at the same height we were launched from, we know the total time is just going to be double the peak time. So, take that value, 1.17, multiply by 2. The total time, 2.34. In the x direction, we know that initial velocity, 16.38. Acceleration in the x is 0. What this lets us do is we can use delta x is initial velocity in the x times t plus 1/2 acceleration in the x t squared. The acceleration in the x is 0. This whole term drops out. We end up with just delta x equals initial velocity in the x times t. Delta x is what we're solving for. Initial velocity in the x, 16.38. We want to use the total time here, so 2.34 seconds. 16.38 times 2.34 seconds gives us a delta x, 38.33. Time it took the ball to eventually reach a vertical velocity of negative 9. Okay. Well, we want time. We're going to use our y variables. Acceleration, negative 9.8. Initial velocity in the y, final velocity in the y. Final velocity, we're looking for negative 9. Let's toss our units on there. Initial velocity in the y is 11.47. We want the time. We can do this with final velocity equals initial velocity plus acceleration times time. Final velocity is negative 9. Initial velocity 11.47. Acceleration negative 9.8. Solve for time. So we're going to take negative 9. We're going to move 11.47 over. Oh. Yeah, this is negative 9. Well, let's clear that up. Okay. And start with 0. And we end up with negative 9. Okay. Now we subtract 11.47. Divide by 9.8. I meant to divide by negative 9.8. But we can divide by negative 1. And let's force that to give us a decimal. The time, 2.089 seconds. A 50-kilogram skateboarder rolls horizontally off the top of a set of stairs 2 meters higher than the ground below. Velocity of the skateboarder the instant it leaves the cliff is 5 meters a second. We have lots of points. They're all moments. In the table below, fill in all blank spaces. Okay. Well, acceleration is never changing. We're just going to write our units once at the top of each of these. Acceleration in the x is always 0. Acceleration in the y is always negative 9.8. Okay. There is a lot to solve for. Okay. This is essentially going to be a lot of the same process. So what I'll do, let me show you the process for solving one of these variables. So say velocity in the y. Well, our first one, it's nice, it's simple. We're leaving horizontally. So at the start, horizontally, we're at rest. What we can do, let's say we'll solve column B. For B, or not column B, but rather row B, we know B has a delta y, negative 0.3. We always know the acceleration, negative 9.8. We know the initial velocity in the y, and our initial velocity will always be 0. If we want to solve for the final velocity, what we can do, and that specifically will solve for this slot right here. What we can do then is we don't have time. So let's use final velocity squared equals initial velocity squared plus 2 acceleration y delta y. Final velocity is something we're solving for. Initial velocity is 0, it's just going to drop out. 2 times negative 9.8 is negative 19.6. Delta y is, of course, our negative 0.3. And we go ahead and we say, okay, the negatives are going to cancel. We get an answer, don't forget to square root, of 2.42. And you might say, well, isn't it negative? It is. You have to remember, when you take the square root, you get plus or minus. We know we're moving downward, it should be negative. Negative 2.42. And as you go down, all the way down, all you're going to do is you're going to end up with this same thing. The only thing changing, initial velocity stays the same, acceleration stays the same. Delta y is what changes. So we'd look at our next one. We'd say, okay, negative 0.8. All that ends up changing is this. We still get our negative 19.6. So for our next one, we'll plug in 19.6 times our 0.8. Take our square root, and we say, okay, negative 3.96. What do you do if you do not have delta y, right? We can go ahead and do this. 19.6 times 2. Take the square root. Negative 6.26. Let's continue. How do you solve for something like the time? Well, the time, you can really use a lot of your different variables that you have. You can say, I think the easiest way to do it, once you have that final velocity, you can just use final velocity is equal to your initial velocity plus acceleration times time. If our final velocity is negative 2.42, that initial velocity is 0, we're really going to be consistently just taking our final velocity and divide by our 9.8. Now keep in mind the negatives will cancel out, so the time here is 0.25 seconds. 3.96 divided by 9.8. 0.40 seconds. You could do this in the reverse. Take that initial velocity, acceleration, and if you have a time, say take the time of 0.46 seconds. We know that initial velocity is 0. So 9.8 times 0.46, we know that velocity will be negative. We find out, okay, this velocity, negative 4.51. 9.8 times 0.55, negative 5.39. Delta x and velocity x, we have to get a little bit later. We can keep going. Let's make sure we're still recording. Alright, how do you get, say, a delta y? Well, again, depending on what you have, if you have your final velocity, acceleration, and time, you could solve. You could say something like, we'll just separate this out. Delta y is initial velocity in the y times t plus 1/2 acceleration in the y t squared. Now that is a lot of plugging in. Another way you could find delta y would be using, say, this equation, but that involves squaring. I do think that equation is a little bit simpler, because you say final velocity in the y squared equals initial velocity in the y squared plus 2ay delta y. Honestly, both of these are pretty workable, because your initial velocity in the y direction is 0, so these terms cancel. And honestly, I think I like this one slightly more. 1/2 of your acceleration in the y would be negative 4.9. If you plug in your time, so say we're solving for this spot, we'd say our time is 0.46, and we square that. 0.46 squared times 4.9, delta y negative 1.04. Take our time, 0.55, square it, times 4.9, negative 1.48. Alright, and at last we reach the section F. delta x is 3. Meters higher. Excellent. The velocity of the skateboarder the instant it leaves the cliff is 5. So, since they're moving totally horizontally, that velocity is in the x. And the acceleration in the x is 0. These are all 5. So, for, say, this slot, how do we get the time here? Well, use your x variables and say delta x is equal to your velocity in the x times t. Solve for t. Delta x is 3 divided by your velocity gets you your time. 0.6. Use what we've learned. Solve for your, say, delta y. Take time, 0.6 squared. Multiply by 4.9. This gets negative 1.76. To find velocity in the y, take the time, 0.6 times 9.8, negative 5.88. How do you solve for everything else? Well, you can keep using delta x right here. If we want our delta x, take your velocity in the x, 5, multiply by time. So, 0.25 times 5. This is 1.25. 0.4 times 5. This is 2. 0.46 times 5. 2.3. 0.55 times 5. This is 2.75. How do we get our last bits of information? Well, we're looking for time, we're looking for delta x. Let's find time first. We'll use time to solve for delta x. To find time, have we done that before? Looks like we have not. Okay. Well, actually, oh yes. Yeah, I did write out an example. I swore I had to have written out an example. Plug in your final velocity. So final velocity in the y. These are negative 6.26. Divide by that acceleration in the y. Negative 9.8. The negatives go away, and you figure out, oh, your time here must be 0.64. Take your time, multiply 0.64 times your velocity in the x, and we get our delta x 3.2. Alright, last section, energy. What is the law of conservation of energy? That is just saying that energy cannot be created or destroyed, so energy must be conserved. If there is no work done on a system, the total mechanical energy of that system stays constant. In some situations, total mechanical energy of an object increases. You have 3 situations in which this can occur. Alright, well, if I push an object, say I push a box to the right, the kinetic energy goes up. So here I am, I'm pushing a box to the right, kinetic energy goes up, total mechanical energy goes up. I did work, I gave the system energy. I could pick something up from the ground, and I could raise it up. I don't know how many arms I'm giving myself, but I could raise it up to some height off the ground, increasing its gravitational potential energy. Again, I did work increasing the energy of the system. If I take a rubber band and I stretch it, here's a rubber band that's normal, here's a rubber band that's stretched. If I stretch it, I have again done work on the rubber band, giving it some of my energy. Total mechanical energy can decrease. If we add a box speeding along, maybe I stand there. I stop it, decrease the energy. negative work. I lower the box down. Gotta draw my 3 arms. And we could say I take that stretched rubber band and I bring it back to neutral. All the equations. Alright. Well, GB is MGH. KE. That was a horrible K. KE. 1/2 mv squared. Total mechanical energy is GPE plus KE plus EPE. We do not have an equation for EPE. We know work is a change in energy, and we know work is force times distance. We also know power is work over time. Lots of variables. Let's talk through them. M, mass, measured in kilograms. G, acceleration due to gravity, measured in meters per second squared. Height, height of an object off some ground or off the point you decide to call 0, measured in meters. Velocity, measured in meters per second. Energy, or work, measured in joules. Force and distance, force measured in newtons, distance measured in meters. Power measured in watts, work in joules, time in seconds. Give an example of a force being applied to an object but no work being done. If you push on a wall, it is not gaining or losing energy. Furthermore, even though you're applying a force, the wall is not moving a distance, so no work is done. An object moving but no work being done. Well, if we carry something horizontally, so here's something. If we carry it like this, it is at, say, a constant speed and at a constant height. No energy changes, no work is done. Force being applied to a moving object, no work being done on that object. Same example we had above. If you have, or what we will talk about, is if you have a force and you apply a force, say, to the right, say you're pushing a box, this does positive work. When the force and distance point in the same direction, positive work is done, energy is added into the system. When the force and the distance the object move are opposites, this does negative work. Energy is taken out of the system. So say a box sliding towards you, you push it the opposite way, it slows down, you did negative work, you took energy away from that box. Or if you have, say, a force that is perpendicular to the direction the object is moving, this does 0 work. So just like the example, if you pick something up, you're applying a force up on the object as you move to the right. The distance is to the right. The force you apply is up. These are perpendicular. It does no work. Alright, hopper popper reaches this height. Draw a picture of the popper's flight. Label energy types. Launch position, halfway to the top, at the top. Okay, energy types. Draw a picture. Cool. Okay, so here it is soared. Here it has popped. Here it is halfway to the top. And here it is at the top. This will be 1, 2, 3, and 4. At 1, it is all elastic potential energy. At 2, no more elastic potential energy, just kinetic. 3, kinetic, it's still moving upwards, and it has GPE. At 4, it is just GPE, as it is no longer moving. What is the elastic potential energy the popper stores? Well, we can set the energy at any of these points equal to all the other energies. There's no work done. Energy must be conserved. So let's say that elastic potential energy at point 1 must be equal to the GPE at point 4. So that elastic potential energy, the GPE is mgh. We'll plug in the mass of the hopper popper, 0.4. G is 9.8. The height it reaches is 2.3. We'll go through and we will say, okay, 0.4 times 9.8 times 2.3. It was storing 9.016 joules of elastic potential energy. That energy, from step 1 to step 2, gets turned entirely into kinetic energy. It doesn't go anywhere else. So, we can say that elastic potential energy turns into the kinetic energy at point 2. We know the elastic potential energy was 9.016. Kinetic energy is 1/2 mv squared. So we'll go ahead and take our 9.016, multiply by 2, divide by the mass of 0.4, and take the square root. And we find our velocity, 6.7 meters per second. Speed of the hopper popper when it is 1 meter from the ground. Okay, again, elastic potential energy. Total mechanical energy is always always constant here since there's no work. Our total mechanical energy is our 9.016. It turns into kinetic energy plus GP. The elastic potential is 9.016. Kinetic energy is 1/2. The mass, which is 0.4, v squared, that's what we're solving for. GP is the mass, 0.4, times 9.8, times the height off the ground. Now we go through, we do our math. 0.4 times 9.8 times 1. This is 3.92. This is 0.2 v squared. This is 9.016. Subtract 9.016 minus 3.92. We end up with 5.096 equals 0.2 v squared divided by 0.2, and take the square root, and we find that velocity should be 5.05 meters per second. That makes sense. That's less than it was right when it launched, as it has gained some GPE, so thus lost some KE. And speed when it's 1.5 meters from the ground. Really same exact setup. We're just going to say this is 9.016 equals 1/2 0.4 v squared plus 0.4, 9.8. Now our height is 1.5. Go ahead and figure out what this is. 0.4 times 9.8 times 1.5, 5.88. This is 0.2 v squared. This 9.016. So we take 9.016, subtract 5.88, divide by 0.2, take the square root, and again, our velocity is continuing to shrink as we gain height. Velocity is decreasing. This makes sense. We know from projectiles, our acceleration for a projectile is downward. We should be slowing down as we move up. And from energy, we know we're gaining GPE. Our total must stay the same, so we must be losing KE. Alright, home stretch. While dribbling a 0.45 kilogram soccer ball, you give it a kick and increase its speed. Work done by your foot on the soccer ball. Work is a change in energy. Any change is final minus initial. We started out. Our final energy is just kinetic energy. Initial energy is still just kinetic energy. Find these out. Final kinetic energy is 1/2 the mass times that velocity. Okay, excellent. I want to make sure I haven't been forgetting anything. Cool. Okay. Velocity squared, again, this is final velocity, 1.7 squared, minus Kinetic energy, it had to start with 1.2 squared. Plug in, and we can find out our answers. 1.7 times 1.7 times 0.45 divided by 2. 0.65. 1.2 times 1.2 times 0.45, cut in half. The work is 0.326 joules. Power of your foot. Power is work over time. The work was 0.326. Time is 0.2. Power is 1.63 watts. Hot wheel car rolling towards a hill. Bottom of the hill, it is traveling 8. What will its height be when it is slowed down to 2? Okay, so we start with energy. And we're starting here, we're going up. At the bottom, we have just KE. As we're going up, we have GPE and we have KE. So we'll say the kinetic energy we start with must be equal to that kinetic energy we end with plus GPE. Again, maybe we label this is point A, this is point B, and we can write out our equation, 1/2 the mass, 0.05, velocity squared, velocity at the bottom is 8. We know it slows down to 2. We're just solving for that height. And again, we're going ahead, we're plugging everything in. 8 times 8 is 64 times 0.05, cut it in half, 1.6. 2 times 2 is 4. This energy is 0.1. And then we get 9.8 times 0.05, 0.49 each. 1.6 minus 0.1, divided by 0.49, height 3.06 meters. Excellent. Last page. Small roller coaster train, pictured below. How much battery do I have? Excellent. Has a mass of 60 kilograms. At each location, label what types of energies are present. Look at the table for hints about location A. At A, we have height and velocity, so we have KE and GPE. At B, we're at the very bottom, just KE. C, we have KE and GPE, and at D, we have KE and GPE. Okay. We'll use our equations. Remember, GPE is mgh. KE is 1/2 mv squared. So let's find our energy at A. We can find, since we know the mass, we can find our gravitational potential energy. The mass is 60 times 9.8 times our height of 13. That gives us a gravitational potential energy, 7,644. Kinetic energy is the velocity, 0.2, squared, times the mass of 60. And we're cutting that in half. 1.2. Slightly different amounts of energy. Times 0.2 times 60 divided by 2. Okay. Total mechanical energy is then 7,645.2. That total mechanical energy must be conserved. There's no work done. So that energy is not changing. When we have no height, we have no gravitational potential energy. All of our energy is kinetic. If we know the height, we can solve for GPE. So 60 times 9.8 times 7 subtract from the total 4,116 to get our kinetic energy. How do we find these velocities? Well, use your kinetic energy formula. Plug in your kinetic energy, multiply by 2 to cancel the half, divide by the mass in 60, and take the square root. That gets us 15.96 right here. And 2 divided by 60, square root, 10.85 right here. Something's not right. .1 times 10.1. This is 30,060.3. Okay, let's double check. Alright. So we keep going. Take our total mechanical energy, subtract by our 3060.3 KE, and we find our GPE. And now you might say, okay, Mr. Rosauer, why is GPE increasing, going from C to D? Well, that's because we've drawn the picture incorrectly. Really, D should be somewhere up here, right? It's gained height, going from C to D. That's why it has more GPE. But nevertheless, we can solve for velocity. And now we know, oh, if we're actually lower down at C, it should be faster. Which is what we find, 3529.2. Multiply that by 2, divide by the mass of 60, take the square root, and we get 10.85. I know that doesn't match what we have in the key. If you take a look at our key, you'd say, oh, we have these same values, right? You can see GPE is clearly increasing. Kinetic energy is decreasing. But here, for decreasing kinetic energy, we're going faster. The velocity, again, we made a mistake in the key. The answer should be this. And we can take a look at our height at D, plug in your gravitational potential energy, divide by the mass, divide by 9.8, and we get that higher height, about 7.8. Now we can tack on units. Height is meters, velocity meters per second, and all energies are joules. Final problem. When an archer pulls on a bow, elastic potential energy is stored in the stretched bowstring in a manner similar to a rubber band. When released, that stored energy is transferred to the arrow. In the diagram, 4 locations are labeled on the arrow's path. A and C have the same height. Position D is the instant before the arrow reaches the ground. Approximately 450 joules of elastic potential energy can be stored in the bowstring. Explain why the arrow cannot have 450 joules of kinetic energy at location B. Well, it's going from EPE and GPE to KE and GPE to then KE and GPE to then just KE. It stores 450 joules of elastic potential energy. Right when it is released, all of that elastic potential energy turns into kinetic energy. But then it gains height. When it gains height, it loses kinetic energy. So as it gains height, some of that 450 joules of elastic potential energy turned into GPE, some of it turned into KE. Give a set of possible values for UG and KE. That is supposed to say gravitational potential energy. and KE at locations B, C, and D. Okay, potential values. Well, we'll say if we have 450 joules of elastic potential energy. Let's say, again, set of possible values. Let's make up some numbers. So if we have 450 joules elastic potential energy, let's say we have 1,000 GPE. That also means we have 1,000 GPE here, right? Our total is the same. So we're saying our total right here. Again, I just made these numbers up. Our total would be 1,450. So the KE right here would be 450. Say we've gained 200 GPE up here. That means our KE would only be 250. And our KE right down here should be 1,450. And that's it.